Okay, we're going to move on to section 3.3 now. So 3.3, this is all about something, zeros of polynomial functions and the rational zeros theorem. So first we're going to start with something called the factor theorem. And what the factor theorem says is for any polynomial, say the polynomial's name is f of x, x minus k is a factor if and only if the function's output when the input is k is 0. So we're going to use the factor theorem for this first example. So we want to see, is x minus 1 a factor of, in part A, the function f of x equals 2x to the fourth plus 3x squared minus 5x plus 7. And in part B, I'm going to leave a little bit of space for synthetic division there. And in part B, f of x equals 3x to the fifth minus 2x to the fourth plus x cubed minus 8x squared plus 5x plus 1. So to do this, if x minus 1 is a factor of this function, then that would imply that f of 1 equaled 0. So what we're going to do is to figure out f of 1, we're going to do synthetic division on these polynomials. We're going to use the remainder theorem that out here at the end the remainder will be f of 1, and we can check and see if the remainder is 0 or not. If it is 0, then f of 1 is 0, so x minus 1 is a factor. If it's anything else, then it's not a factor. So we put 2 for x to the fourth's number. We're missing x cubed, so I use 0 as a placeholder. 3 is x squared's number. Negative 5 is x's number. 7 is the constant term. So bring down 2. 1 times 2 is 2. That adds up to 2. 1 times 2 is still 2. That adds up to 5. 1 times 5 is 5. That adds up to nothing. 1 times nothing is 0. This adds up to 7. So this right here, this is f of 1. And so we get, that is not equal to 0 because it's equal to 7. So we get x minus 1 is not a factor. So this first one, x minus 1 is not a factor. We did synthetic division. The remainder told us f of 1, and f of 1 did not equal 0. So in this one, to see if x minus 1 is a 0 of this function, we got 3 for x to the fifths, negative 2 for x to the fourths, 1 for x cubed, negative 8 for x squared, 5 for x's, and 1 for the constant term. So we'll do synthetic division. Bring down a 3. We get 3, 1, 1, 2, 2, negative 6, negative 6, negative 1, negative 1, and we get remainder 0. So this is good. This is f of 1. So f of 1 equaled 0, which says x minus 1 is a factor in this situation. We got x minus 1 as a factor. Okay. So that is how to use the factor theorem. You kind of combine it with the remainder theorem, and you use synthetic division, and you check if the remainder of the division is 0. If it is 0, that's good. It's a factor. If it's not 0, that's bad, and the thing you're dividing by is not a factor. So for our next bit here, we want to factor a polynomial given a 0. So this is example 2. So they want us to factor f of x equals 6x cubed plus 19x squared plus 2x minus 3 given negative 3 is a 0. So this is where we're going to use that second form of the division algorithm. We're going to use dividend equals divisor times quotient plus remainder. So So we're going to use this form of the division algorithm to help us factor. So since they told us negative 3 is a 0, I'm going to do synthetic division with negative 3 out to the side. I know I'm going to get 0 back as a remainder because they told me negative 3 is 0. So I bring down 6. Negative 3 times 6 is negative 18. That adds up to 1. Negative 3 times 1 is negative 3. That adds up to negative 1. Negative 3 times negative 1 is positive 3. That adds up to 0. So that's what we wanted. And now the dividend was the original function f of x. That equals the divisor, which negative 3 represents the divisor, was x plus 3, times the quotient, which this is constant term of the quotient. This is x's number. This is x squared's number. So we get 6x squared plus x minus 1, plus remainder, which is going to just be plus 0. So what we do here is, in order to factor our expression, now that we use the division algorithm, we were told to 0, we have it to a degree 1 times a degree 2 polynomial. We can just factor the degree 2 polynomial using regular factorization techniques. So this will be, let's see, it'll be a 1 and a 1. Needs to add up to positive 1 and multiply together to negative 1. So the thing that becomes 3x gets a positive 1. The one that becomes a 2x gets a negative 1. And this is our fully factored form of that polynomial. Okay, so next we want to write out the rational zeros theorem, and then we're going to do an example that uses it. And then we got a couple other examples to talk about from this section. So for rational zeros theorem, so we're going to write this out. This is going to look kind of weird, and then we'll show you how to use it. So we say, if P over Q is a rational number, written in lowest terms, and if P over Q is a 0 of f, where f is a polynomial function, with integer coefficients, then P is a factor of the constant term and Q is a factor of the leading coefficient. Okay. So we're going to kind of talk through how to use this in the next example. So we kind of use this the reverse of how it's stated. We look at all factors of P, all factors of Q, and then we can generate a list of all P over Q's, and numbers that are zeros of the function would be on that list, or some of the numbers that were zeros of the function would be on that list. So we'll kind of talk through that in this example here. We want to, we're given f of x equals 6x to the fourth plus 7x cubed minus 12x squared minus 3x plus 2. Part A, they tell us to list all possible rational zeros. So this is where we use the rational zeros theorem. And then part B, they want us to factor f of x and find all zeros. So part A gives us a list of possible zeros, and then in part B they want us to figure out what of those possible zeros actually are zeros. So for part A, this is going to be using that rational zeros theorem we wrote down. P is going to be factors of the constant term 2, and Q will be factors of the leading coefficient 6. So P we kind of think of as being 2, Q we kind of think of as being 6. I need to write down all numbers that divide evenly into 2, which will be plus or minus 1 and 2. I need to write down all numbers that divide evenly into 6, which is plus or minus 1, 2, 3, and 6. Then I need to generate all P over Q's, all combinations with one of these P values in the top and these Q values down in the bottom. So this will be plus or minus, it'll be 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third, 1 over 6 is a sixth. Then we'll have 2 over 1 is 2, 2 over 2 is 1, 2 over 3 is 2 thirds, 2 over 6 is really 1 third. So this right here is our list of all possible rational zeros. Okay, part B wants us to factor the function and find all actual zeros. So since we started with the degree 4 function, we're going to need to do synthetic division twice to find 2 zeros, and then we can factor the remaining amount. If it was an x cubed for the leading term, we'd only need to find 1 zero with synthetic division, then we can factor. If it was an x to the 5, we would need 3 zeros, then we could use synthetic division factor. So what I do is I load in my numbers for my function for a synthetic division. I'm going to start with different numbers on my list, and I'm looking for remainder 0. So I have 6, 7, negative 12. So 6, 7, negative 12, negative 3, and 2. And looking through my numbers, I'm going to start with the easiest numbers on the list. So I'm going to start with positive 1, then I'll look at negative 1, then I'll start with positive 2, then negative 2, then I'll go into the fractions if I need to. So start with positive 1. I bring down 6. 1 times 6 is 6. 7 plus 6 is 13. 1 times 13 is 13. Negative 12 plus 13 is 1. 1 times 1 is 1. Negative 3 plus 1 is negative 2. 1 times negative 2 is negative 2, and negative 2 plus 2 ends up being 0. So if we look at what we're left with in the quotient, this is no x's number, this is x to the first power's number, this is x squared's number, and this is x cubed's number. We still have a degree 3 polynomial down there, and I don't know how to factor 6x cubed plus 13x squared plus x minus 2. The factor by grouping techniques and other stuff like that won't work on it. So this is why I said we needed to find a second 0 before we can factor. So to get the second 0, you're going to chain it off of the first division. And I'm going to continue on in my list. I'm going to look at negative 1 next and hope that that works. If it doesn't, I'll back out of it and I'll try positive 2. And then I'll back out of that, try negative 2 until I find one that does work. So bring down 6. Negative 1 times 6 is negative 6. When I say mean that works, I mean one that gives me back remainder 0. This gives me negative 7. That is a negative 6. This is a positive 6. That's a 4, so that's no good. We don't want that, so I need to back out of negative 1. Negative 1 didn't work, so let's try 2. It's the next easiest number to work with. I don't really want to put the fractions in there unless I have to, because synthetic division with fractions is a little bit trickier than just with whole numbers. So bring down 6. 2 times 6 is 12. That is a 25. We're up to 50. That's a 51. We're up to 102, and then that's 100. That is not 0, so we need to go back again. Say, okay, positive 2 did not work. Let's try negative 2. So bring down 6. Negative 2 times 6 is negative 12. This is 1. That will make a negative 2. That will be a negative 1. This will make a positive 2. And there we go. So it took us a little bit to get there, but we found our second 0 that worked. Now, if we look at what's the quotient, we have no x power, we have x to the first power, and we have x squared. So we know how to factor that. We just need to kind of unpeel the information that we got here. So the dividend is f of x. The first divisor 1 says that there is a factor x minus 1 there in the factorization. The second one we found to work was negative 2, which means that there's a factor x plus 2. And then the remaining stuff is 6x squared plus x minus 1, which I can factor using regular factorization techniques. So we get x minus 1 times x plus 2 times, we're going to break this up as 3x and 2x. The thing that pairs up to become 3 needs to be positive 1, and the thing that becomes the 2 needs to be negative 1. So here's our fully factored form of that function f of x. And then each of these creates each of these factors creates a 0. X minus 1 creates the 0 at 1, so that's our first actual 0. X plus 2 creates a 0 at negative 2. If I put a third in here, 3 times a third is 1. 1 minus 1 is 0, so a third is our next 0. And then negative a half would be the final 0. And on these last terms, if you weren't able to look at it until it's negative a half, you could set the whole 2x plus 1 equal to 0 and start solving it for x. And then you set the whole term equal to 0, you can solve it for x, and that'll get you the x value that you want. So here's the factored form, here's the 4 zeros, and we have our rational zeros theorem problem wrapped up like that. Next thing we're going to do is do a couple of fundamental theorem of algebra and number of zeros theorem, and then we're going to use that to build up some polynomial functions. And then we have a couple kind of finishing out the section stuff, and then we'll wrap up our section. So for fundamental theorem of algebra, we say every function defined by a polynomial of degree 1 or more must just be a 1, I guess we'll write it that way, 1 or more, has at least one complex 0. Also, we get the number of zeros theorem. Which number of zeros theorem says the following thing. A function defined by a polynomial of degree n has at most n distinct zeros. Okay, so we're going to use combine some of these ideas together to solve the next example, and then after that we got a couple more ideas, and then we'll get our last example or two. So this example, we want to find a polynomial of degree 3 with real coefficients that satisfies following things. Part A, so we want one function with degree 3 with real coefficients that has zeros of -1, 2, and 4. And they also want the function evaluated at 1 equals 3. So we'll give some space for that. And then part B wants us to do a -2 is a 0 of multiplicity 3. And then they want f of -1 to equal 4. So to solve this, we're going to write out our function. We'll say, all right, f of x equals, when you all have a statement like f of 1 equals 3 or f of -1 equals 4, we're going to have to include a leading value a that we're going to have to calculate. So we're just going to put an a down because see f of 1 has to equal 3. And then we're going to create, for each of these zeros, we're going to create a factor that created the zeros. We're going to use the same idea we used up here, like 1 came from the factor x minus 1, -2 came from the factor x plus 2, a third came from 3x minus 1, and -1/2 came from 2x plus 1. So we're going to use this idea and kind of work from the bottom back up one step. So if I want a 0 from at -1, that had to come from a factor x plus 1. A 0 at 2 came from a factor x minus 2. And a 0 at 4 came from a factor x minus 4. So we got our zeros figured out. Now we need to go through and figure out how do we make f of 1 equal to 3. So this is going to be where we solve for a. So we're going to say, all right, f of 1, that will equal a. Now x is 1, so that's 1 plus 1, 1 minus 2, 1 minus 4. F of 1 is supposed to be 3, so we get 3 equals a times 1 plus 1 is 2, so that's a times 2 times 1 minus 2 is -1 times 1 minus 4 is -3. This says 3 equals a times, let's see here, that is going to be 6. So if I divide the 6 across, 3/6, which equals 1/2. So a, this says a is 3/6, which reduces down to 1/2. So we got our a value as 1/2. So now that we know our a value is 1/2, we're going to rewrite our function. F of x equals 1/2 plugged in for the a value times the first factor times the second factor times the third factor. This thing is degree 3 because we had 3 linear factors, and each of those 3 linear factors will produce a 0. It'll produce the 3 zeros we wanted, and the a value being 1/2 will make f of 1 equal to 3. So we've got everything that the expression or the statement wanted us to do. So moving down here, -2 is a 0 of multiplicity 3, and we want f of -1 to equal 4. So we'll say f of x is going to equal to a times, if -2 is a 0 of multiplicity 3, that means the x plus 2 factor needs to be counted 3 times, which you all could write as a times x plus 2 cubed. Now we want to find f of -1 equals 4. So we'll say, all right, let's look at f of -1. That will be -1 plus 2 cubed. F of -1 equals 4, so 4 will equal a times -1 plus 2 is 1. So we get 1 cubed, which just says 4 is a, since 1 cubed is 1. So now that we know 4 is a, we're going to rewrite our function with the correct value plugged in for a. So f of x equals 4 times x plus 2 cubed, and that is our expression. Does everything we want, has 0 with multiplicity 3 because we counted it 3 times, counted its factor 3 times. F of -1 equaled 4. We did that by solving for the a. Since it has 3 linear factors, it is degree 3 and has real coefficients. So we're done there. So next we got a couple of things about the complex conjugate, and then we'll finish up with last 2 examples. So this is going to be a property of complex conjugates. So if we have C plus D the complex conjugate of c plus d, that's the complex conjugate of c plus the complex conjugate of d. If we have the complex conjugate of c times d, that will equal the complex conjugate of c multiplied to the complex conjugate of d. And this bar above this represents the complex conjugate. And remember from section 1.3, if we have a plus bi, this has complex conjugate a minus bi. And the final one says if you have complex conjugate of c to the n, that is the same as the complex conjugate of c raised to the nth power. So these are a couple little properties of complex conjugates. In this section, we're not going to use these just a whole lot, but they're good to kind of keep around. What we're going to use mostly right now is the conjugate zeros theorem. So what the conjugate zeros theorem says is if f of x defines a polynomial having only real coefficients and if z equals a plus bi is a zero of f, then z bar, which is a minus bi, is also a zero of f. Okay, so we're going to use this idea to do the next problem. So next example, they want us to find a polynomial called f of x of least degree having only real coefficients and has zeros at 3 and 2 plus I. So, since we want the polynomial to have real coefficients, if 2 plus I is a 0, we need its complex conjugate 2 minus I also a 0. This is because they said it needs to have real coefficients. If they said the coefficients can be complex, then we don't need to include this, but since they said we need real coefficients, we have to include it. When we were building up the other problems, this time they don't have any f of 1 equals 3s or anything like that, so we can skip the a values we were using here when we had a f of 1 equals 3 or f of negative 1 equals 4 condition. So they didn't tell me like f of 2 equaled 7 or anything like that, so I don't need an a. I'm just going to write down x minus 3. This creates the 0 at 3. I need a factor that creates a 0 at the first complex number. So it's x minus 2 plus I. Then I need an x minus 2 minus I to create a 0 at the second complex number. And this right here will be a polynomial that has real coefficients that does everything the example wants us to do. So we have one last example we're going to look at, and then that'll wrap this section up. So our final example here, they're going to say, suppose you have a function f of x which equals x to the fourth minus 7x cubed plus 18x squared minus 22x plus 12, and they want us to factor f of x given 1 minus I is a 0. So we're going to have some scratch work when we go through to solve this because we have a complex number. That'll make the divisions a little messy in parts. So, since our polynomial here has real coefficients, that's going to force us to get 1 plus I is also a 0. So now I know two things that are going to be zeros of my function, so let's go through and do the work. So I'm going to do my work kind of over here, and I'm going to try to leave myself some room for scratch work. So we're going to put a 1 minus I, the first 0, out there. We'll use 1 for x to the fourth number, negative 7 for x cubed, 18 for x squared, negative 22 for x, and 12 for the constant term. So bring down 1. 1 minus I times 1 is just itself 1 minus I. Negative 7 plus 1 is negative 6, and we get the minus I still. Now I need 1 minus I times negative 6 minus I. So I'm going to do this in scratch work over here. We choose a slightly different color. So we want to do 1 minus I times negative 6 minus I. If I FOIL that out, I get negative 6 minus I plus 6I. That'll be plus I squared. Plus I squared is negative 1, so this will be negative 7. Negative I plus 6i's is plus 5i's. So I get negative 7 plus 5i there. 18 take away 7 is 11, so I have 11 plus 5i. Now I need to do 1 minus I times 11 plus 5i. So we get, okay, what is 1 minus I times 11 plus 5i? So 1 times 11 is 11. 1 times 5i is plus 5i. Negative I times 11 is negative 11i. Negative I times 5i is negative 5i squared. Negative 5i squared is going to become a positive 5. 11 plus 5 is 16. 5i's take away 11i's is minus 6i's. So we get 16 minus 6i's. Negative 22 take away 16 is negative 6 minus 6i. So now I do 1 minus I times negative 6 minus 6i. So we get 1 minus I times negative 6 minus 6i. Let's see, so it's negative 6. That'll be a negative 6i. That'll be a positive 6i. That will be a positive 6i squared. This cancels. This becomes a negative 6. Negative 6 minus 6 is negative 12. So I get remainder 0, which is what I wanted. So now I need to chain the second number that we know is going to be a 0, which is 1 plus I, off of that first division. So I bring down 1. 1 plus I times 1 is 1 plus I. Negative 6 plus 1 is negative 5. Negative I plus I cancel out. 1 times negative 5 is negative 5. I times negative 5 is minus 5i. 11 take away 5 is 6. 5i minus 5i cancel out. 1 times 6 is 6. I times 6 is plus 6i. Negative 6 plus 6 is nothing. Negative 6i plus 6i is nothing, so we get down to 0 there. So what we're currently at from this division is our function f of x. It equals x minus the first complex number, 1 minus I, times x minus the second complex number, 1 plus I. This is no x's number. This is x to the first power. This is x squared. So out here it's times x squared minus 5x plus 6 that we can factor. So our goal is to fully factor this function. We're really close now. We say, all right, we have the x minus 1 minus I term. We have the x minus 1 plus I term. And then here we got the x minus 2 times x minus 3 term. And that will fully factor our degree 4 polynomial. So that wraps up section 3.3, and we're going to stop there.